तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Next part of continuum mechanics which we are going to study, that is the constitutive equations. We have studied all the background that is required for understanding the constitutive equations. We have talked about the thermodynamic principles that should be satisfied by the constitutive equations. We have talked about the objectivity, and though we have not talked at length about other principles like determinism and the effect of the neighborhoods and so on, though we are not going to go into the details of the theory of constitutive equations per se, we are in a good position to understand the available constitutive equations. Now let us look at, as the first part, what we call as the elastic materials. Though you would have studied the elastic materials to be a, I would say, a material where when you remove the loads, then suppose I have a say material like this, and then when I remove the load, it regains its original position. This is what you would have studied as probably as the elastic material. You will find that the way we are going to define elastic materials, especially under this kind of large deformations, finite deformations, are going to be very different. Now let's see how we are going to define. We are going to say that the elastic materials can be represented, note this carefully, can be represented by means of two different formulations or two different schools of thoughts. One is called as hypoelastic or hyperelastic. So the first thing you have to notice is that hypoelastic materials are not something separate elastic materials. It is not like hypoelastic materials are rubber, hyperelastic materials are say steel or something like that. No, hypoelastic and hyperelastic materials are a way of representing elastic materials. They are two schools of thought. Okay, hypoelastic materials are also called as Cauchy materials, and hyperelastic materials are also called as green elastic materials. So this is a school of thought which was put forward probably by Cauchy. We don't have historic background for it, and then carried over. And the other one is from by Green, A. Green, and so they are called as hyperelastic materials. Hyperelastic materials are ones which respect thermodynamic principles, or in other words, which follows thermodynamic principles. The hypoelastic materials start at a different level, where it just puts down the relationship between stress and strain. Many times you would find that hypoelastic approach, if I can call that as an approach, or an hyperelastic approach, if you will find that both of them take you to the same result for many of the materials. But since the approach of hypoelasticity is not that very sound, in fact purists do not agree with hypoelastic material, most of us look at only hyperelastic materials for further analysis. Right. So we will abandon the hypoelastic theory for the time being. I shouldn't say that everyone has abandoned it. There are situations where people use hypoelastic theory. Okay, but let us now proceed in this course with hyperelastic theory or hyperelasticity. Note that hyperelasticity is just a name that is given for elastic materials, okay, and usually we refer to them when they undergo large deformations. It is not that elasticity is different, hyperelasticity is different, and so on. Okay, when an elastic material undergoes large deformations, then we classify or we call them as hyperelastic materials, because these materials has to undergo certain rules and regulations which we are going to see now. One of the easiest, even more than that, the nicest way of representing or calling an elastic material, a material to be elastic, is to say that the material does not dissipate energy. Or in other words, if you had noticed, or if you go back to our thermodynamic class, you would find that we had written the dissipation, okay, to be consisting of two terms. One is P colon F dot, where of course you know that P is the first PLR Kirchhoff stress, and F dot minus psi dot. What is this psi which we had introduced? Helmholtz free energy, but usually this free energy is called as strain energy. Okay, the terminology that is most of the time you use that as strain energy itself. So strictly speaking, what we had introduced is a free energy at that place. And if I remove all the thermal terms from it, then you would see that this term should be greater than or equal to 0. Now, if this term happens to be equal to 0, if this term happens to be 0, then there is no dissipation of energy, which means that the process is completely reversible. It's completely reversible. Now, through the other two, I would say the principles, you can write actually psi to be a function of deformation, which is represented as F here, so that this equation now can be written as P colon F dot. I hope you know there's a contraction product. There's a contraction, and P colon F dot is nothing but Pij Fij. Pij Fij, and you can in fact write it in a matrix form also as trace of P transpose F dot and so on. Okay, so minus psi dot can be written as dou psi by chain rule dou F colon F dot is equal to 0. Or in other words, P minus is equal to 0, and which leads us to an important relationship which can be written like this. First pk stress is the gradient of or is the dou by dou f of the strain energy. So that's a very important, probably the most important step in the whole development of constitutive equations. Now, how do we define different materials? So we said that an hyperelastic materials ultimately is one which follows or which respects the thermodynamic principles, which means that a hyperelastic material is one which follows all these steps, and which of course means that a hyperelastic material is one which has the relationship written here. Is that clear? So that is the hyperelastic material. The question that may come to your mind is, I know of elastic materials, say for example elastomers or rubber, that's a elastic material. We know most of the biological tissues, say skin or your heart muscle, calf muscle, all these things are again elastic materials. And again you know that, see, even some of the cell structures, they are all elastic materials. So you know a number of practical, if I may call it practical within quotes, materials which are elastic. Okay? Hence, according to our definition, should also be classified as hyperelastic because they undergo large deformations. And of course, a set of metals in the elastic region, which are again are elastic materials. Again, elastic materials. If that is the case, do they all undergo or do they all respect this law? Yes, they all respect this law. But then what is the difference between them? What is the difference between them? On one hand, I have this equation. Okay, on the other hand, I have practical materials which satisfy this equation. Of course, I know that the deformations induce different types of stresses in different materials. Okay? So where do I actually draw the line and say that, look, the elastic behavior of rubber is like this. The elastic behavior of steel is like this. The elastic material of biological tissue is like this, and so on. Where do I draw a line? Where, or in other words, to put it in a more simple fashion, I know that from a very, very early class that sigma is equal to E into epsilon, and that this kind of simple elastic, linear elastic rule is valid for all metals, whether it is in the elastic region, of course, whether it is steel or whether it is copper, whether it's aluminum, and so on. And I also know that the value of E changes from one material to the other. Value of nu also has is also different when I say, for example, take titanium and steel and so on. So what is the analogy now between this and this? Now the analogy is not very straightforward, it's a two-step process. So in other words, we have on one hand hyperelastic material, okay, satisfy this equation. On the other hand, we have a number of types of what we call as strain energy functions. This is the function, psi function of F, strain energy functions. Okay, these strain energy functions may be, say, Ogden, Mooney-Rivlin, Neo-Hookean, Yov, and so on. So these are the strain energy functions that are available. See, this may vary, okay, and let me write down one function. Say, for example, if you look at a Mooney-Rivlin function or say Ogden function, then I can write down the strain energy function. Actually, in terms of stretch, usually you write this in terms of stretch, say lambda 1, lambda 2, and lambda 3, and then this is, though I'm preempting some things, you may not understand it completely, just I want to put down this, because why did I get stretch here, we will see that later, but all of you know intuitively that stretch, okay, means deformation, okay, so I can express it in terms of lambda 1, lambda 2, and lambda 3, okay, so this will be defined as a mu p sigma mu p by alpha p into lambda 1 alpha p plus lambda 2 alpha p plus lambda 3 alpha p minus 3, okay, something like this, where alpha p and mu p, where p varies from say 1 to n, n can be 2, 3, 5, and so on. So this kind of equations are the ones, okay, which define what we call as the strain energy function. If you look at another, say, for example, Mooney-Rivlin, then Mooney-Rivlin psi can be written as a C1 I1 minus 3, okay, where I1 is the first invariant. And if you, sorry, this is for Neo-Hookean. If you look at Yo's model, then Yo's model has the strain energy function to be written as C1 into I1 minus 3 plus C2 into say I1 minus 3 whole squared plus C3 into I1 minus 3 cubed, and so on. Okay, you can write down a set of equations like this for different size put forward by different people looking at the physical behavior at the same time saying that certain other conditions are satisfied. Please note that most of these theories which we are dealing with are macroscopic theories. Now, there is no attempt right now to, in this course of course, to link this macroscopic theory with the microscopic theory of what happens inside. For example, it's very clear that C1 is some constant, alpha p is some constant, C2 is some constant, and so on. So how do you get these constants? What are they? They are obtained more from a phenomenological approach, and right now we do not link this up with the microscopic aspect. We will come to that later. Okay. So the approach which we are dealing with are what are called as the macroscopic or phenomenological approach. So these are the materials that are available. Okay. Note the word, common word, hyperelastic material, Ogden material, Mooney-Rivlin material, and so on. It doesn't mean Ogden material means physically there is a material. All materials which can be expressed in terms of Ogden strain energy function is called as the Ogden material. All materials which can be satisfied or which can be written in terms of Yo strain energy function is called as Yo material, and so on. Is that clear? All of them can be written in different types of things. See, on the other hand, the third column is the actual material. This can be rubber, a carbon filled rubber used in tires, okay, a rubber for say tires. It has a special chemical composition and compound. Then you have, say for example, biological materials, say heart muscle, and so on. List of actual materials. The big picture is all of them are of course hyperelastic materials. The second picture is that each one of these materials can be represented as one or more of the middle column of materials. Rubber can be represented as Ogden material, not very accurately using a neo-Hookean material. Okay. Some of them, for example, rubber for tires can be represented exceedingly well with Yo as a Yo material, not so very accurately as Mooney-Rivlin material or Ogden material, and so on. In fact, when you come to heart muscle, the type of strain energy function is totally going to be different. So you, as a next step, what you do is you now build connection between the actual material and the mathematical representation of its behavior put forward by Ogden, Mooney-Rivlin, and so on. Now let us say that I can represent it using Ogden material, say a rubber, even a heart muscle. There has been a paper 1983-84 where, or why 84, even in recent times, where the Ogden material is used to represent the heart muscle. Now then, how do I distinguish these two materials? Come back to this place. Yes, that's true. So both of them have the same relationship, okay, but these constants differ from one material to the other. So I hope the whole complex structure of hyperelasticity is clear now. If there's any question, I'll answer that.
How can I represent it? How can I know that it can be represented by Ogden model or Mooney-Rivlin model? Yeah,
see, when you have a material, you should know certain of its behavior, okay, definitely, okay, before you can attempt to represent it using one of these materials. Now there are reasons why, for example, rubber for tires is exceedingly well represented by Yo's model, because the shear modulus with deformation, it varies and is supposed to have a double peak. So that kind of mechanical behavior can be represented in a much better fashion using Yo's model. For example, if you take a heart muscle, there is a strain energy function by Hunter, Okay. Now he has looked at the mechanical behavior of the heart muscle and said that, look, if this is the behavior, then this is the type of strain energy function which is closest to the behavior. Or in other words, all classes of heart muscles can be represented now using this type of behavior, this type of strain energy function. So there have been people who have been working on this for a very, very long time, the constitutive equations, how to put forward strain energy functions. So when you take a material and when you want to analyze it using nonlinear finite elements, the first thing you should do is, how do I represent this material? So suppose you go back and look at packages like, say, Abacus, you will see that they have different materials that are there. I mean, they have different materials to represent the actual physical materials, or material models to represent actual physical models or physical materials. They call this as material model. So for example, if you take Abacus, you will have Ogden material, you will have Yo material, you have Mooney-Rivlin material, and so on, material models. So when you want to take, say, want to go and analyze tire, the first thing to do is, now what is the appropriate representation model for this tire rubber which goes into the tire? Okay, so you have to really understand how it behaves. Maybe go back and look at the literature, you find that people have put down Yo's model specifically with a purpose in mind. Okay, Yo put this down maybe if I remember right, it's in the early 90s. So then you go and apply Yo's model. In order to apply that, one of the very, very important things in nonlinear finite element is that you need constants. This testing of many of these materials are quite, I wouldn't say difficult, but time consuming, and in fact it requires a lot of effort. Now there are actually routines that are available. If you take Abacus, routines that are available even to fit these constants. How do you get these constants? You do a series of tests. What are these tests? Uniaxial test. If you do a uniaxial test, you can fit certain of these constants. Maybe you have to do a biaxial test. Okay, you can improve some of them. Then you may have to do a shear test. Then you will improve, you will get a much better understanding, and so on. So in other words, the testing of these materials, which means that we are interested in the mechanical behavior, not in how, say, the structure inside, the isomers or whatever is inside, how it behaves. We are not interested in that. Mechanical behavior, okay, on a gross scale, on a macro scale. So you have to understand them using all these kind of test results and then fit these kind of constants to a particular equation. Okay, that's why I said there are routines available. But for some of them it's very simple. Neo-Hookean, it's very simple. It's not very difficult to fit this. You need much less tests. When you need much less tests, okay, that means that all the different types of mechanical behaviors are really not covered by that material. That's what it means. Okay, is that clear? Fine. So that completes and that gives you an overall picture of where we stand with respect to the hyperelastic materials. Okay, so with that in mind, let us look at other considerations that should be there in order to define the strain energy function. I'm not going to go into a lot of details here because constitutive equation itself is a big topic, and you can offer a course on the constitutive equations and strain energy functions. I'm not going to do that, but I'm going to give you an overall flavor in the next two classes as to how these representations actually are there for different materials. So if you look at the constraints that we may have to put, all these things are very straightforward. They are not very difficult to understand. So let's say, what are the constraints? The constraint is that F, of course, F cannot be 0. If it goes to 0, what does it mean? That means that you're trying to annihilate or shrink the material to almost, or make it almost disappear, which means that the energy that you require in order to do that is enormously large. So the one thing is that when f tends to 0, then the psi of f tends to infinity. We use infinity to mean that it's very large. We use 0 to mean that they are very small. Same fashion, when I make f go to infinity, what do I mean? I mean to say that I'm going to increase the volume material enormously, which means that f going to infinity means that psi f also has to be extremely large. So either way, the psi f, this strain energy function has to be large. That's one thing. The other is with respect to objectivity. Let us say that I am looking at, or you are looking at it as a new observer. The function will not change. It's an Ogden function. It has to be the same. If it has to have those constants, then the constants have to be there, and so on. But your objectivity means that there's a relationship between the f star or your f and what I observe. We already know that. Both of us should have the same function, hence, so that this can be written as, the function can be written as QF. QF. So necessarily the function should be written in such a fashion that the function is not changed when you post multiply f by an orthogonal tensor Q. If we choose this orthogonal tensor to be R transpose, then this happens to be, and from the relationship that f is equal to RU, R transpose f is equal to U, of course R transpose is equal to I. So which means that we get a very interesting and very important result, that the strain energy function is now a function of only the stretch part of f. Stretch part of f. Remember that f had two things in it. One is the rotation part, represented by R, the stretch part represented by U. In fact, I would have been very worried if I had stopped here, okay, and that since R is already present there, if I had to now have my function to be a function of R as well as U, I would have been a bit worried. Okay, why? Because then I can just rotate a piece, and if this strain energy function respects it, then I would get a stress. After all, P, the Euler-Kirchhoff stress, is a function of the dou by dou f of this function. So fortunately it doesn't happen like that, and so actually this function is a function ultimately reduces to a function of only the stretch alone. So in other words, function of U. Is that clear? Okay. Now before we proceed, we'll look at one more aspect of the material behavior and this objectivity, what we call as anisotropy. The question that comes to our mind after looking at this is that what is the connection between anisotropy and objectivity? Or in other words, what we said here is that when there is a rotation, the rotation does not affect the behavior of the material, or the response is not affected by the rotation. But we have not completed the story yet. But we know that there are materials which are anisotropic. typically most of the composite materials are anisotropic materials. What do I mean by that? I mean to say that there are fibers which run in these composite materials, and that the deformations are function of the relationship between the fibers and your loading and so on. Suppose I take this, I apply the load, composite material, it behaves in one fashion, but load applied in another direction, okay, it behaves in a different fashion and so on. Now that means that you have a vague notion that when I rotate the specimen and I apply the load, my deformations are going to be different, okay, but how is that related to the subjectivity? Now in other words, what we mean to say is that suppose I have a material or I have a component, okay, and then there is a deformation due to some loading, and let me call this as the reference configuration with X, and that now there is a new reference configuration. Say, let me call this as X0, no, X is enough, and so this is X star, okay, and there is again a deformation, let us say like this. Then if it happens to be like this, then we call this material as an isotropic material, Now what is the condition for isotropic materials? Simple, it's not very, quite easy to understand that. So in other words, F, which is say dou x by dou capital X, should be the same whether I start my journey from here or here, okay. So when there is a difference in my reference frames, is what I said when I rotate it and then deform. So I'm going to define first isotropic material, and one which does not satisfy the law which I'm going to put down are called as anisotropic materials. So that is equal to say dou x by dou x star by dou x. And noting that the relationship between x star and x is quite straightforward. So for example, I can write x star to be q x, so that dou x star by dou x, okay, can be written as q, so that the second equation here, or second part of the equation here, can be represented as q, so that dou x by dou x star is f star, so this becomes f star q, or in other words, f star is equal to f q transpose. But note the subtle difference between f star here and f star what we had for objectivity. So this is a condition for isotropic material, Note the difference between the two. In this case, I have f to be post multiplied by q transpose, note that. So I have f to be post multiplied by q transpose. In the previous case, I had f to be pre multiplied by q. So there is a difference between anisotropic material and anisotropic and isotropic material. Is that clear? Right. But physically, what does it mean? Physically, what is this post multiplying and pre multiplying and so on? That's very important to understand what physically it means. Physically, it means is that what it means is that the isotropic materials are ones where if I take the reference configuration, rotate the reference configuration and apply this loading, or without rotation if I apply the loading, in both cases my deformation is going to be the same, right? So that is what I mean by saying that this equation is satisfied. On the other hand, what do we mean by objectivity? What do we mean by objectivity? Objectivity means that if I now load the material, okay, come to this state with the deformation, with the loading in place. Now if I now rotate this, which is equivalent to an observer rotating, because two observers have the same reference configuration. When they look at the reference, they are at the same level. That's why if you remember, we got f star is equal to qf. If you go back and look at how we got for objectivity, you will remember that we got objectivity to be f star is equal to qf, basically because we assumed that the observer looks at the reference configuration in the same fashion. Both the observers look at the reference configuration in the same fashion. So if you now take this deformed fellow here and then rotate it, which means an observer observing the deformed configuration separately. So deformed configuration, the observer will get x star. Then my results is objective if it follows that three conditions which we had put down in one of our earlier classes. So the difference between anisotropy and objectivity is that in objectivity we are looking at x and x star. In anisotropy we are looking at x and capital X and capital X star. Is that clear? Now having studied this, let's get back to certain other issues which are important for us, okay, and see how we can represent this. Now that we know that the strain energy function is a function of u alone, which means that the strain energy function is a function of C, which means that you can also say that the strain energy function is a function of E. So you can say that function of C, function of E. Note that usually you use the same symbol, function, the same symbol, whether it is C, E, or whether it is U. We use the same symbol here. C, what is the C? We remember defined F transpose F, okay, to be C, and we had a relationship between E and C. What was the relationship? Half into C minus I is equal to E, or 2E is equal to C minus I, and so on. So all those things, because of this relationship, you can say that the function can be in terms of C or E and so on.
Because it's a function of U, then you're saying that it can be a function of C.
Yeah, since it's a function of U, I'm saying that it can be looked at as a function of C, it can be looked at as a function of E, and so on. Now, as we had done in our earlier classes, I have to. These we are now right now talking about. Please note that we are talking about material objectivity. These results are due to material objectivity. Okay, so if psi f is equal to, or psi f star, which is okay, let me write that. If it so happens that then we say that the material is isotropic. Now having done all this work, let us see how do we develop the relationship between P and sigma and so on. See, because ultimately if you look at all these codes, you would see that they express the results only in terms of the Cauchy stress, because Cauchy stress has the most meaning as far as our interpretations are concerned. So we always talk about the quantities in the material frame as well as the quantities in the spatial frame, right? Talk about both. So let us see how we develop the relationship between them. So let us now go back to psi dot, and psi dot can be written as f dot, which can be written as trace of dou psi by dou f transpose f dot in terms of the matrix notation. Now if I now express psi in terms of C, then you can write that down also as trace of dou psi by dou C transpose C dot. Now what is the relationship between C dot and F dot? Because I need this, we'll come to that in a minute, but what is the relationship between the two? Let's see. What is C dot? Can you just write down? Since you asked a question, what is C? Can you write down what is C is equal to F transpose F. So C dot is what, and then substitute it back here, okay, and see how we can represent psi dot. This is equal to so substituting that C dot into this expression and noting that C is symmetric, we can write down the equation here to be equal to 2 times trace of dou psi by dou C transpose F transpose F dot. Since transpose is the same, since it is symmetric, I can remove that and say that 2 times dou psi by dou C F transpose F dot. Now noting the relationship between P and sigma, I can write down sigma to be, let's say, how we write down the sigma to be in terms of P, in terms of sigma in terms of P, J inverse F P transpose, right? Just go and have a look. Dou psi by, that's in other words, dou psi by dou F transpose. Which now, using this relationship, you can write that down as, look at this here, the two relationship between them. So you can write that down as dou psi by dou C F transpose. So sigma 2 times, of course, is equal to 2 J inverse F dou psi by dou C F transpose. J inverse P F transpose, but P transpose, both of them are the same, okay, so that's why, because sigma is equal to, note that sigma is equal to sigma transpose, hence whether you write it as P F transpose or the other way, it will be the same, because sigma is equal to sigma transpose, right? So that is the relationship between sigma and dou psi by dou C. Yeah, what I did was to replace from here, okay, look at this expression, okay, this and this, compare this and this, so F dot is common, so the rest of it with 2 should be equal to dou psi by dou F. So when I express it in terms of C, then actually it is 2 into dou psi by dou C F transpose, and that's what I've substituted, okay. Right. So our next goal is to now develop what is the relationship between Yes, second P law Kirchhoff stress. See, I have already said this, that the first and the second P law Kirchhoff stress are very important, though first P law Kirchhoff stress has a lot of physical meaning to it. Okay, we know what it is, it's a nominal stress. Unfortunately or fortunately, we do not use first P law Kirchhoff stress to that extent in computational engineering. You tell me why? Very good. So it is not symmetric. So most of the situations we use only second P law Kirchhoff stress, and it's very important that we develop what is the relationship between second P law Kirchhoff stress and these quantities. By the way, P is, of course, as someone said, P can be now, P is equal to, what's it from here? In terms of, if psi is expressed in terms of C, then what is P? 2F dou psi by. Now, what is the relationship between S and P, and so that you express this S as, note that, what is the relationship between S and P? Can you just write that down? Note that down, what it is. So you will write this down as 2 of dou psi by dou C, of course. And noting the relationship between E and C, we say that this is equal to, and that's a very, very important relationship. So S is equal to, if I express the strain energy density function in terms of E, then dou psi by dou. If you remember, okay, we had approximated S to be sigma and E to be epsilon, and in fact, in the last course, we had just said sigma is equal to dou psi by dou epsilon, strain energy function, because of the small deformation case that was involved there. So you get that important relationship between the strain energy density function and the second P law Kirchhoff stress. So as a next step, we now look at, so having studied the background, so we can be now fast, we can move forward. As a next step, we look at now work done, okay, in a closed cycle and why hyperelasticity. Just with that one small goal, we can move forward and look at various functions, how they are written, and so on. So we'll stop here, and we'll continue with the rest of our discussions on constitutive equations in the next class.